faithfully delivering value, exploring great books worldwide.
Hello, this is Sally's Book Talk.
Today's featured book is 7 Brief Lessons on Physics. Among all natural sciences, physics undoubtedly reveals the essence of our world most profoundly. British physicist Ernest Rutherford once remarked, "All science is either physics or stamp collecting." This implied that compared to physics, other natural sciences were merely at the level of stamp collecting. Such a statement was bound to offend scientists from other disciplines.
The most intense backlash came from chemists, who retaliated by awarding Rutherford a Nobel Prize in chemistry.
Most people's understanding of physics remains rooted in knowledge from over a century ago. What's taught in high school physics textbooks mainly covers pre-20th century concepts. In reality, scientists have constructed an entirely new edifice of physics since the 20th century. Recent decades have seen numerous popular science books explaining this new framework. Examples include Stephen Hawking's 1988, A Brief History of Time, and another book that reigned global interest in 2014.
That's the book I'm introducing today. 7 Brief Lessons on Physics.
First published in Italy in 2014, it sold 300,000 copies in its debut year. In 2015, it dominated the New York Times bestseller list and was named Book of the Year by The Guardian and The Economist. It's now translated into over 30 languages. The author, Italian physicist Carlo Rovelli, has a remarkable life story. During university, Rovelli was imprisoned for participating in student political activism. After earning his doctorate, he was briefly detained again for refusing military service. Shortly after release, Rovelli co-founded loop quantum gravity theory with 2 other physicists, becoming a pioneer in this field. In this concise 100-page work, Rovelli uses poetic yet clear language to explain modern physics breakthroughs since the 20th century. The first lesson, titled The Most Beautiful Theory, discusses Einstein's general relativity. The second lesson, Quantum, discusses quantum mechanics, one of the 2 pillars of 20th century physics. Subsequent lessons explore cosmic particles, black holes, and other concepts derived from these 2 foundational theories. Now, I'll introduce these 2 fundamental and crucial theories, general relativity and quantum mechanics. Let's start with the first theory, general relativity. Many people feel intimidated just hearing its name. Actually, general relativity could alternatively be called Einstein's theory of gravity. First, let's trace the historical development of Einstein's gravity. In the 17th century, Newton discovered universal gravitation after his famous apple incident. He proposed that all matter exerts mutual gravitational attraction. To complete his theory, Newton introduced the concept of space as an immense container holding the universe, where objects move under gravitational influence. But if we ask, how does gravity actually arise? Newton himself couldn't answer this question. In the 19th century, British physicists Faraday and Maxwell enriched Newton's framework with the concept of electromagnetic fields. Electromagnetic fields are generated by moving charged particles specifically. Accelerating charges create time-varying electric fields. These time-varying electric fields then generate magnetic fields. The time-varying magnetic fields, in turn, produce electric fields, forming a self-sustaining electromagnetic field through mutual interaction. Electromagnetic fields permeate space, vibrating like ripples on a lake to propagate electromagnetic waves. Familiar phenomena like visible light and radio waves are all forms of electromagnetic radiation. In the early 20th century, Einstein unified gravitational and electromagnetic concepts through his theory of gravitational fields. However, unlike electromagnetic fields, gravitational fields don't exist within space. They constitute space itself. In Einstein's framework, Newton's motion containing space and his own gravity transmitting field became identical. Thus, space transformed from passive background into active participanta, mutable, bendable component of physical reality. We're no longer confined within an invisible rigid framework, but immersed in a vast flexible entity that can bend. In reality, it's the curvature of space that creates gravity. This concept might initially sound abstract. Let's explore it through a thought experiment. Imagine an extremely flat mattress with a small glass ball rolling across it. Without external interference, the ball would maintain straight-line motion. Now, place a massive iron ball on the mattress. It immediately creates a depression. If our glass ball now passes near the iron ball, its trajectory visibly changes. With sufficient initial velocity, the glass ball could escape this gravitational well. With lower velocity, it would spiral along the curved surface until collision. Now, let's engage your imagination. Doesn't this curved motion resemble the glass ball being gravitationally attracted?
The resemblance is striking, isn't it?
Let's reinterpret mattress becomes space-time, glass ball as Earth, iron ball as sun. Einstein demonstrated the sun's mass warps space-time, creating what we perceive as gravity. So how does gravity actually emerge? Massive objects curve their surrounding space-time, and this curvature manifests as gravitational effects. Space-time curvature is gravity's origin, the cornerstone of Einstein's theory of general relativity. General relativity made several extraordinary predictions. The book details 4 key predictions, beginning with space-time curvature. The sun's massive curvature explains planetary orbits, and Alea even bends light passing nearby. In 1919, Arthur Eddington's eclipse expeditions confirmed light bending precisely as predicted, catapulting Einstein to global fame. Time itself warps near massive objects. General relativity predicts time flows faster, closer to the sun. In regions farther from the sun, time progresses more slowly. This prediction was confirmed in the 1960s by Harvard's gravitational redshift experiment. The second prediction of general relativity concerns black holes. When a massive star exhausts its fuel, it explodes catastrophically. The remaining core collapses under gravity, creating extreme space-time curvature that forms a cosmic void. This cosmic predator lurks in space. Approach too close, and not even light can escape. Since no light escapes its vicinity, black holes remain invisible. American physicist John Wheeler named these terrifying objects black holes. Scientists detect them through gravitational effects rather than direct observation. Astronomers now believe black holes abound in the universe, with a supermassive one at our galaxy's core, weighing 4 million solar masses. The third prediction, cosmic expansionism, emerged from Friedman and Lemaitre's work showing space cannot remain static. In 1929, Edwin Hubble confirmed the universe is indeed expanding. If the universe expands now, it must have originated from an extremely dense state. This backward extrapolation led to the Big Bang theory, cosmic expansion triggered by an ancient explosion. The Big Bang left behind a relic radiation called the cosmic magging background, CMB. In 1964, Bell Labs engineers Heinsius and Wilson detected the CMB, confirming the Big Bang and earning them the 1978 Nobel Prize. The fourth prediction, gravitational waves, was Einstein's own 1916 proposal. He suggested space-time could ripple like water surface waves. These space-time ripples are what we call gravitational waves. When gravitational waves pass through, everything from rulers to planets undergoes periodic stretching and compression. Detecting gravitational waves is extremely challenging due to their minuscule effects. For perspective, a ruler spanning 100,000 light-years, our galaxy's diameter would only deform by about 1 meter under gravitational waves. Remarkably, on September 14, 2015, LIGO made humanity's first direct detection of gravitational waves. Within 18 months, physicists Rainer Weiss, Kip Thorne, and Barry Barish received the 2017 Nobel Prize for this breakthrough. A century later, all of general relativity's predictions have been experimentally confirmed. This verification earned general relativity its reputation as the most beautiful theory. This beautiful theory guides cosmic exploration while impacting daily life through technologies like GPS navigation systems, which require relativistic corrections for accuracy. Now, let's explore quantum mechanics, developed collaboratively, versus Einstein's solo work on relativity. What exactly is quantum mechanics? Let me explain through analogy. Our daily experience exists in the macroscopic world. Countless phenomena here obey Newtonian mechanics. Beyond this lies an invisible microscopic realm. This subatomic world contains fundamental building blocks, molecules, atoms, and particles. These quantum particles follow different rules. Quantum mechanics. Essentially, quantum mechanics is the Newtonian physics of the microscopic world. In his book, Rovelli outlines 4 pivotal stages in quantum mechanics development. First stage: Planck's discovery of quantized light energy. Max Planck, recognized as quantum theory's father, revealed that heated objects emit electromagnetic radiation in discrete packets. Visible light, we know, is actually a form of electromagnetic radiation. In 1900, Planck studied radiation emitted from a heated black body. To calculate energy distribution across frequencies, Planck made a radical assumption: light energy exists in discrete quanta packets. This meant light energy wasn't continuous, but composed of quantum building blocks. This hypothesis completely contradicted conventional wisdom. Though calculations matched experimental data perfectly, Planck himself couldn't explain why this worked. Second phase. Einstein proposed light consists of particles 1905, answering Planck's dilemma. Thus, Einstein became quantum mechanics' adoptive father through his photoelectric effect research. The photoelectric effect, discovered by Hertz in 1887, shows light ejecting electrons from metals. This makes sense as light transfers energy to electrons, enabling escape from atomic bonds. The mystery effect depends on light frequency, not intensity. Einstein solved this by proposing light consists of photon particles carrying frequency-dependent energy. Higher frequencies photons carry more energy to liberate electrons. Sufficient photon energy means immediate electron emission. Low-energy photons can't free electrons regardless of exposure duration. This threshold resembles university admission cutoffs. Meeting Tsinghua, Peking U score means instant admission. Falling short means rejection despite repeated attempts. Quantum mechanics, like all children, eventually forged its own path as it matured. Neither its biological father Planck nor adoptive father Einstein could control its development. Quantum mechanics entered its third developmental phase. Bohr discovered electrons and atoms have quantized energy levels, like photons, a fundamental quantum property. Bohr theoretically analyzed hydrogen structure, proposing his revolutionary atomic model. This model perfectly matched observed hydrogen spectral data. In this model, electrons orbit nuclei like planets around stars. Crucially, these orbits were quantized, restricted to specific energy levels. Electrons could only occupy discrete orbits, like runners confined to lanes. Lower energy orbits closer to nucleus, higher energy farther out. Similar to rocket launches, higher orbits require more energy. Electrons jumping between orbits emit, absorb specific photons, quantum leaps. Microscopic particles defy Newtonian mechanics entirely. Fourth phase. Heisenberg's uncertainty principle revealed electrons lack definite positions until measured. Like Nerno's shadow clones, electrons exist probabilistically in multiple locations. Heisenberg's principle became quantum mechanics' cornerstone, guiding mathematical formalism. Quantum mechanics explains periodic table patterns through wave equation solutions. It enabled transistors and integrated circuits, foundations of modern computing. Relativity's essence, space-time curvature as gravity, quantum's core, uncertainty principle. Rovelli concludes, humans aren't cosmic center, uniqueness lies in fictional concept collaboration. As Yuval Harari notes in *Sapiens*, shared myths enable larger-scale human cooperation. Rovelli argues, humanity's distinction is curiosity driving exploration from Africa outward. This same curiosity fuels scientific discovery and natural science development. Let me conclude with Rovelli's closing aphorism. At the frontier of human knowledge we navigate uncharted oceans. The world's mysteries and beauty dazzle us with their radiance.
This concludes our journey through 7 brief lessons on physics. Find key takeaways below the audio. Until next time.